Hello. So we've done basically all the theory around kind of trajectories and stuff, and I thought it'd be really nice to do. I'm going to ease you in gently. We'll do quite a simple example, okay, of finding the trajectories of this linear system of autonomous equations. Okay, so we've been given find the trajectories of these are the things which have been given: dx by dt equals y and dy by dt equals x. Hopefully, you can see these two things are both linear. Okay, and remember whenever we've got a linear thing, we've got ax plus by plus k1. This is just sort of the general form of it, and we have cx here plus dy plus k2. Okay, well hopefully you can see. Well, actually, I'll come on to this in a minute. Basically, what we want to do is combine these two equations into one equation, and we do that, if you remember, by writing dx by dt equals ax plus k. Okay, so we can combine this in kind of matrix notation, combine all of our equations, all of our differential equations into one nice, neat little thing, one nice little equation over here. And so our vector x is just x and y, okay, because those are just our variables. Now, what's a? Well, a, if you remember, is a, b, c, d, which is why I wanted to write this out. Well, if you look, in this first term, what's a? Well, there's no x term. So therefore, a has to be 0. Okay, so a goes here in this top left corner. So there's no x term here, it's just a y. So a has to be 0 to get rid of that x term. And then if you can look, there's b is just clearly 1, because we've only got a single y, so therefore b has to be 1, so b goes there. Now let's look in here. So we're just looking at c and d now. Well, there's an x term. There's just one single x, therefore c has to be 1. And there's no y term, so therefore d has to be equal to 0. Okay, and then what about k? Well, if you have a look, k, there's no constants hanging along there. There's no constants tagging along. So therefore k has to just be 0, 0. Both k1 and k2 are just 0, 0. Now, if you remember that if k is just 0, 0, then that automatically implies that our equilibrium point is equal to 0, 0 as well. Okay, but I am just going to check that. I'm going to verify that in case you don't believe me, because this is the correct way of doing it. Okay, so dx by dt, we're going to set that equal to 0. So we're going to basically set y equal to 0. Okay, fine. And then we've got dy by dt equals 0. So therefore we've got x equals 0. So basically what we've got is x equals 0. So our equilibrium point, this is how we get our equilibrium point, by setting our derivatives equal to 0. Our equilibrium point is just x equals 0, y equals 0. Well, that's kind of what we predicted over here. So it does work. Okay, so the next thing which I want to do is try and plot these things on a trajectory map. Now, you can do it directly if you're really clever. You can do it by doing dy over dx, okay, and that's going to give you x over y, okay, and then you can solve it by doing separation of variables. So this is just a kind of a by thing. So this is going to be integration of y dy is equal to the integration of x dx. I'm just basically moving all the y's on this side. So this y I'm going to move up there, okay, and this dx I'm going to move up there, and I'm just integrating both sides. So that's what I'm going to end up there, and then I'm going to get y squared, half y squared is going to be equal to half x squared, plus my constant of integration. Multiply everything through by 2. I'm going to end up with y squared is equal to x squared plus c. This is still going to be a constant, even if it's multiplied by 2. And then I'm going to end up with y squared minus x squared is equal to c. Okay, and then if you wanted to have a look at that, then you might be able to plot that directly if you really wanted to. But I'm going to do it the long way, because I think that's the way which I feel most comfortable with. And the long way is basically looking at the eigenvalues of this matrix. So I've got A is equal to 0, 1, 1, 0. Okay, and I want to basically find the eigenvalues of this matrix. So actually I'm going to write it down here. I'm going to take this and write it down here because it's getting a little bit messy. So there we go. I want to basically find the eigenvalues of this matrix. Well, remember, we find the eigenvalues of the matrix by doing determinant of A minus lambda I and setting equal to 0. Okay, so what's A minus lambda I? Well, A minus lambda I is going to be 0 minus lambda. So it's going to be minus lambda there. And then, 1 minus 0, so that's going to be 1. It's going to be 1 minus 0, so that's going to be 1. This is going to be 0 minus lambda here as well. Okay, and set that equal to 0. And actually, find the determinant of this. We write the determinant just with straight brackets like that. It's just a notation for it. So what's the determinant of this matrix? Well, it's going to be minus lambda times minus lambda. You happy? That's just going to be lambda squared. Okay, minus 1 times 1, so that's minus 1, set that equal to 0. That implies that lambda squared is equal to 1, which implies that lambda 1 is going to equal to 1, and lambda 2 is going to be equal to minus 1. Remember that when we take the square root, we can have positive or negative of that root. So these are just our two eigenvalues now. We've got lambda 1 equals 1, and lambda 2 equals negative 1. So the next thing which you want to do is find the corresponding eigenvectors. And remember, we find the corresponding eigenvectors by solving the equation A. I'm reluctant to use x as such. I'm going to actually use u, I think, because I've used x above. Okay, so lambda u. Okay, but this, you've probably seen it as ax equals lambda x, but I'm just going to write it like that. So when lambda equals 1, so lambda 1 equals 1, okay, I'm going to end up with, so I've got a, which is 0, 1, 1, 0, u, which is just my variables, x and y, okay, that's going to be equal to 1 times my variables again, so u, my variables, x and y. I should really write x, I'll write x above it, I'll tell you what, I'll compromise. Okay, but I'm reluctant to use x because this is kind of my general points, but I want to differentiate my general points from, or distinguish my general points from my eigenvectors. So that's the reason why I'm using u. Okay, and then let's do the same thing over here for lambda 2 equals, what's this, minus 1. So I'm going to end up with 0, 1, 1, 0, multiplied by my variables x, y. Okay, and that's going to be equal to negative 1 times my variables x, y. So I'm going to solve these two equations. So I'm going to end up with 0 times x plus 1 times y, and that's going to be equal to 1 times x. Okay, and then if I do this one, I've got 1 times x plus 0 times y is equal to 1 times y. Okay, so in other words, for lambda 1 equals 1, I get the eigenvector u1, and that's going to be equal to just xy. Okay, and then for lambda 2, what am I going to end up with? Same thing again, so I'm going to end up with 0 times x plus 1 times y. It's going to be equal to negative 1 times x, so negative x. And then I've got 1 times x is equal to, plus 0 times y, plus is equal to negative 1 times y, so negative y. So I can choose any value. Okay, you can see these are exactly the same thing. So I'm going to choose the first one. I'm going to end up with lambda 2 equals negative 1. So when my eigenvalue is at negative 1, my eigenvector is going to be, one of them is going to be negative xy. Okay, so now I can try and plot what's going on. So I'm going to draw my plot in. So it's going to be x against y, x against y. I know that my equilibrium point is going to occur here in the centre. This is my equilibrium point. It's the origin, 0, 0. So I showed that above. I showed that up here, or up here. Okay, so my equilibrium point will be at 0, 0. Then I'm going to use these things to work out what's actually going on. Before I can do that, actually, I'll draw it out again, I think. I need to solve my general equation. So x of t is going to be equal, if you remember, c1 e to the lambda 1t u1. This is just my general equation for this thing. So e to the lambda 2 t u2. If you don't remember where that comes from, go back and have a look, okay, at my former videos. But I know that basically I'm looking for a general solution of this kind of type because I've not got complex eigenvalues. Alright, and so my solution is going to be c1 e to the lambda 1. Well, lambda 1 is just 1, so it's going to be 1 times t, and then u1, which of course is just xy, plus c2 e to the lambda 2. Well, lambda 2 is negative 1, so it's going to be negative 1 times t, so it's going to be negative t. u2, one of them is going to be negative, negative xy. I could have x negative y if I wanted to. But now actually I've got everything which I need to, because I know that lambda 1 is 1 and lambda 2 is negative 1. Well, look, this one's positive and this one's negative. And if you remember, we go back to our case. When they're both real numbers, one's positive, one's negative, that will always correspond to a saddle point. Okay, it's just basically what the saddle point is going to look like now. And we're going to use to work out what the saddle point is going to look like, we're going to use this general equation here. Okay, so we're going to use this general equation here to work out what's going to happen as t tends to infinity. So I'm going to draw my plot out. So it's only a very, very rough plot. So I've got x against y, my equilibrium point at the origin again. So I'm going to plot my two eigenvectors on first. That's the first thing we should do. So my first eigenvector is xy. So in other words, the line y equals x. That can be thought of like that. So it's like that. Oops. There we go. And the other one is going to be y equals negative x. So it's the same thing, but just in the negative direction, like that. Okay, so this is going to be, what's that one? u1. And this one over here is going to be u2. All right. And what's going to happen as t approaches infinity? Well, can you see as t approaches infinity, this one is going to get really, really small. Okay, because there's a negative value there. So as t approaches infinity, it's basically going to be a fraction. And it's going to get smaller and smaller and smaller and smaller and smaller because it's effectively 1 over e to the t. So as this second term is 1 over e to the t. So as this gets, this is the dominant term in this second part. Okay, e to the negative t is 1 over e to the t. So as t approaches infinity, that's going to get really, 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 really small. So in other words, this second term is almost insignificant. But as t approaches infinity, this is going to become really, really big. Okay, so this is the dominant term. So in other words, as t approaches infinity, as we go forwards in time, all of our solutions are going to tend towards this eigenvector. So u1, in other words. So all of our lines are going to basically want to try and look like, as we go forwards in time, all of our lines are going to try and look like our first eigenvector, which is this one here. Okay, so all of our lines are going to start off over here. They're all going to start to try and look like this. They're all going to basically try and come parallel to this line there. Okay, so they're going to come in here and going to try and become parallel to this eigenvector. They're going to come in down here, going to try and become parallel to this eigenvector. Okay, and then it's clearly fairly obvious which directions the arrows should be going in. Okay, and you can see here that we definitely correspond to a saddle point. So that's the trajectory of what we've got there. Hopefully that makes a bit of sense.